Hello everyone, this is CSM16A Public Resources. So this public resource section is supposed to be a chapter of 16A content team that helps to address common misconceptions and also help people or guide people to the CSM16A resources. So since we're going to be addressing common misconceptions and we're only a few weeks into the circuit module, let's talk about something a little more simple in terms of the definitions we've went through. And today I'm going to talk about power because there's a confusing thing about power that I'd like to talk about. So since we're talking about a mathematical metric, which power is, I'd like to first define what is power. And keep in mind that we're talking about power as in circuitry, not like realistic power or something. Okay, let's try to define power. So I found a few definitions online. And I've also found a couple of definitions through the lecture slide. And let me summarize some of the equivalent definitions for you, and we'll try to go over how these definitions are actually similar. So first of all, power can be spoken of as the amount of energy that a component absorbs per second. This means that power is essentially the rate at which we use energy throughout time. So we see that a component absorbs electrical energy because the component uses electrical energy and turns it into something else. For example, it might be heat or it might be some other energy that you can learn more about in the physics class. So the alternative definition for power then is the rate at which electric energy is transferred by a circuit. And what the lecture note presents is a very similar definition, which says power is the rate of usage of energy, or the rate of change of energy is what the lecture note really said, but essentially power is more of the rate of usage of energy. And that actually matters for reasons that we'll talk about later. So now we get this kind of point that power is the rate of usage of energy over time, which means I can also mathematically say that P is equal to dE dt, which means the derivative of energy as a function of time. So actually, now let's think about an easier way to express dE dt. So to deal with energy, I can also think about voltage. The way that voltage or electric potential was defined is the amount of energy needed to move a unit charge across distance. Let me explain this definition later. So what a unit charge is essentially just some charged particle that has 1 unit of charge, depending on what's your unit of charge. And frequently we use Coulomb as a unit of charge. So electric potential, or voltage, is the amount of energy needed to move 1 unit charge across distance, which means that I need this amount of small energy, which is dE, I'll say mathematically, to move a charged particle by a specific distance. So I'm multiplying the amount of charge I have, which is dq, a very small charge, with the amount of energy needed per unit of charge to move across some distance to be equal to the small amount of energy that I need to move charged particles across a distance. So moving something to another place usually requires some energy. You'll see this in a gravitational example. In this case, we're talking about electric potential, which means it takes electric energy to push one charged particle into another place. So now we know that D is equal to dq times V, and that's what the equation really stands for. And to get power as dE dt, what we can do then is to take both sides of this equation to its derivative with time. So I see that there's another dE dt here, which is equal to the power. And P is equal to V times dq dt. Well, we know that the rate of change of charge across time on the circuit component is just the current flowing through it, which is why we're able to say P is equal to V times I, or more frequently you will see P equals IV. So this is where P equals IV, the equation, comes from. Alright. So once again, power is the rate of usage of energy. And its unit is, well, it's the change of energy across time, so its unit is going to be watt, which has a division that makes sense, and that is joules, the unit of energy, over second, the unit of time. So energy over time. Okay. So when we talk about power across a circuit component, because remember, it's circuit components that are using energy in the circuit, we speak of the behavior of a circuit component in two ways. Either it costs energy or it gives the circuit energy. So we're going to translate that into more electrical engineering terms. One is called dissipation. And another one is called supplying. So I'm going to draw a T-chart to try to explain the difference between dissipation and supplying. So when we're dissipating energy, we're costing energy, we're using energy. And because power is the rate of usage, when a circuit dissipates power, P equals IV is positive. So you'll see positive power here. But when a component is supplying energy, the circuit is gaining energy. Power is the rate of usage, but I'm gaining energy instead. So when a circuit component supplies energy, you'll get a negative power from that component. That's because it's not using energy. You can determine whether a component is dissipating or supplying energy using node voltage analysis, because by then you can calculate P equals IV, and depending on the signs of I and signs of V, you'll be able to decide whether the power is positive or negative, and in turn decide whether it's dissipating or supplying power. Alright, made it into the box, I guess. Okay. So let me give you an example. Say that we have a resistor here, and I have a current flowing across it, which I'll say IR, and I have a voltage across it, which is VR. Because the current and the voltage is in the same direction from left to right, I can see that the signs of my I and V are going to be the same when I do node voltage analysis. So therefore, P equals IV will then have a positive value that is yielded, and therefore a resistor will be using power. Once again, this is very, very dependent on the circuit you get, so this is just an example that might not always hold true, but it gives you this idea that if your voltage and current is in the same direction, your power should have the positive sign, which means the component is costing or using energy. So there are two more things I'd like to talk about power. One of them is physics. So we live in a physical world, and there are a couple of costs to that. For example, things have to obey physical laws, and there is no magic. Which is why law of conservation of energy becomes relevant. the law of conservation of energy states that within a circuit, there is a zero net change of energy. What this means is that the rate of change of energy across time is equal to 0. So the total power of an entire circuit is 0. That is pretty important and is pretty useful. We'll be frequently using this fact on the past exam problem walkthroughs. So that's one thing I want to talk about power. The other thing I want to talk about power is there are a lot of more convenient expressions than P equals IV. So, for example, V is equal to IR, which means I can say P is equal to I times IV, so I squared R. Or I can also say P is equal to V squared over R for the same reason. So sometimes these expressions become very useful, and we'll see how we can use these different equivalent expressions in the exam problem walkthrough. So I'm going to shrink my window a little so you can see the full picture of that entire board work. And once we're fine, I'm going to go on to exam problems. So in the public resources, we try to give a mini lecture that talks about a misconception, and hopefully this gives you a sense of how section walkthroughs are in CSM. And then we're going to go through a couple of past exam problems to continue exemplifying the misconceptions that we have been talking about. So let's first talk about this problem, which is from Spring 22, Midterm 2, question 7. So for the first circuit here, we're supposed to calculate the power supplied by the current source. Well, as mentioned before, to find the current and voltage across a component, I'd like to first perform MVA on the circuit. So let me draw the circuit here. Okay, hopefully this looks good enough. And for simplicity, I'm going to label that the current goes in the exact direction that the current source indicates. So IR is the current flowing through resistor, and IS is the current flowing through the current source. Okay, so previously we mentioned that the total power of the circuit, which would be equal to the power of the current source plus the power of the resistor, is equal to 0 for any circuit. Which means that if I want to find the power from the power of the current source, I can say PIS is equal to negative PR. So now I just need to find the power of the resistor to simplify the calculations and find the power for the current source. So first of all, note that the voltage across the resistor is equal to 2 amps, which is IS, or IR, times the resistance of it. And the reason why we know that IS is equal to IR is because of KCL, the Kirchhoff's current law. So let's draw a node here, and you will see that the current flowing into the node, which is IS, is equal to the current flowing out of the node, which is IR. So IS is equal to IR. So once we know that, the voltage across the resistor is essentially equal to IS times 5 ohms, which is equal to 10 volts. Therefore, the power of the resistor will be equal to, now there are two ways to calculate it. Either you can use P equals IV, or you can use V squared over R. And either way, we will end up with the same expression, that the power of the resistor is 20 watt. So a resistor in this circuit dissipates 20 watt worth of power. So it dissipates energy in this matter. Okay, let me try to move this thing here. Okay, so this tells us that the power of the current source is negative 20 watts, which means the current source supplies 20 watts of power. Okay, So that's an example of how we can find the power across a circuit component using no voltage analysis. Now let's also talk about something else, which is another different circuit. So this circuit is a little more complicated, and we're still trying to find the power that the current source supplies. So why don't I try to simplify this circuit a little by putting the two resistors connected in parallel into the same combination. Let me draw this line a little longer so it connects here. So you see that this circuit is the exact same of the circuit I have in the prompt. This 3 bar means congruent, which means the circuit works similarly, or essentially equivalently. So I'm going to simplify the problem a little more, and I'm going to put the parallel resistor as just one resistor. And this resistor is going to be called the parallel resistor, which I'll say RP is equal to 5 ohm parallel RVM, which is equal to 5 ohms times RVM over 5 ohms plus RVM. Okay, so according to the problem, RVM is 5 ohm, which means this is 5 over 2 ohms. We'll talk about that later. That's pretty useful. But for now, let's keep in mind again that total power of the circuit is 0, which is equal to the power of the current source plus the power of the parallel resistor. Let's draw the passive sign convention out again so we can clearly label what's going on. Okay, so once again I find that KCL says IS is equal to IR, which is equal to 2 ohms. So now I just want to find the power of the parallel resistor, and I can multiply -1 by it to get the power of the current source. So the power of the resistor is equal to do I want to calculate the voltage across it again? Yeah, sure, that works out, but isn't there an easier way to just calculate the power without knowing the voltage? And that is called P is equal to I squared R. So I'm going to use P equals I squared R as my shortcut. So power of parallel resistor is equal to the current across it squared times its resistance, which is equal to 2 amps squared times 5 over 2 ohms, and that is going to give me 10 watts. So the parallel resistor dissipates 10 watts worth of power, or costs 10 watts worth of power. It dissipates energy. So the power of the current source then is equal to -10 watts, which means the current source supplies 10 watts worth of power. So here's a small terminology correction. So power is a rate of change, which if you have a positive power, that means you're dissipating energy. But usually we also wouldn't say dissipating power, because power is a rate of change, not something that you can cost. And dissipate is essentially a synonym of cost. So when we say power, we don't necessarily say dissipate power, or we don't necessarily say dissipate power or really gain power. We say positive power or negative power, and that's usually the more mathematically precise diction. But you can use the terminology that communicates what you mean as long as your reader understands it, which is usually the harder part. So in this case, try to stick with the terminology of supplying power or positive power and negative power. So since we have calculated the power of the current source applied in the second circuit, let's look at the last part of the question. So let P naught, which is usually what we call when we say P0, let P naught be the power supplied by the source if the voltmeter is not present, so that's from part 1, and Pi be the power supplied after adding the non-ideal voltmeter, which is RVM, and we can have this circuit from P2, we would like to ensure Pi is larger or equal to 0.8 times P naught, and let's think about what constraint should we put on the value of RVM. Or in other words, what is an inequality that describes the RVM for this above inequality to work? So the objective of this question, then, is to find an inequality about RVM if Pi is larger or equal to 0.8 P naught. And let's also try to write out Pi and P naught. So P naught is our answer from part 1 about how much power is applied by the current source. So that's going to be IS, which is 2 amps, times the resistor, which is 5 ohms. Actually, not times 5 ohms, times the voltage across the 5 ohm resistor. But that's also equal to I squared R, so I can just say P naught is equal to 2A squared times 5 ohms. I also have Pi, and that is equal to, once again, I squared R. But this time the resistor is not exactly 5 over 2 ohm, because this time we actually have RVM as a variable. So we should just write the resistor as the parallel resistance here. So 5 ohms times RVM over 5 ohm times RVM over 5 ohm plus RVM. Okay, so if we have an inequality of Pi and P naught, then we will probably also have an inequality of our RVM as we do algebraic manipulation, which is what we're going to try for now, because the objective of the question is to find an inequality about RVM. So let's say that Pi is larger or equal to 0.8 P naught, which means 2 amperes squared times 5 ohms times RVM over 5 ohm plus RVM. Let me move this to the side. Thank you. So larger or equal to 2 amperes squared times 5 ohms. I have 2 amperes squared on both my sides, so I'm going to cross that off so that I also don't speak of it wrong again. I'm also going to multiply both sides of the inequality by 5 ohms plus RVM, so it's easier to deal with things. Oh, keep in mind that there's a 0.8 here. So 0.8 times 5 ohms is equal to 4 ohms. Okay, so I get that 5 ohms times RVM is larger or equal to 0.8 times 5 ohms times 5 ohms plus RVM. I'm going to simplify this inequality a little. Actually, I have 5 ohms on both sides, so I can still cross the 5 ohms off. I'm going to write this very gently, so that we can show this. And then we eventually will get into an inequality about RVM that is 0.8 times 5 ohm plus RVM, which is equal to 4 ohms plus 0.8 RVM. So I'm going to subtract both sides by 0.8 RVM. And that leaves me 0.2 RVM is larger or equal to 4 ohms. And then I can get a constraint on RVM, which means I get an inequality that describes how large or how small RVM should be. So I'm going to divide both sides by 0.2. That means multiply both sides by 5. So RVM is larger or equal to 20 ohms, meaning that for this inequality to hold true, we must have that RVM is larger or equal to 20 ohms. So the resistance of your voltmeter should at least be 20 ohms such that you can get the Pi as larger or equal to 0.8 P naught inequality working. So I'm going to stop this recording at this screenshot here where you can see everything and maybe pause the video to zoom in with a screenshot. But this is the end of the public resource for this week. See you next time.